Hello everyone and welcome. Get ready to embark on an incredible energy exploration adventure. Today, we're going to dive deep into the fascinating world of energy. We'll look at all the different forms it takes, from the energy of motion to the power stored in a battery, and even the heat that keeps us warm. Have you ever wondered what the difference is between power and energy? Or what all those units like joules, watts, and calories actually mean? Well, you're in the right place, because we're going to decode all those mysteries together. First things first, let's start with the basics. What exactly is energy? In simple terms, it's the ability to do work. It's what makes things happen, from a car driving down the road to a light bulb glowing in your room. One of the most common forms we encounter every day is mechanical energy. This can be split into two main types: kinetic energy and potential energy. Kinetic energy is the energy of motion. Anything that's moving has kinetic energy. Think about a baseball flying through the air, a spinning top, or even the wind blowing through the trees. The faster an object moves, and the more mass it has, the more kinetic energy it possesses. The formula for kinetic energy is 1/2 times mass times velocity squared. It might sound a bit technical, but the concept is simple: more speed and more mass equals more energy. On the other hand, we have potential energy. This is stored energy that has the potential to be converted into another form, like kinetic energy. Imagine holding a ball up in the air. It's not moving, but it has gravitational potential energy because of its height. If you let it go, that potential energy is converted into kinetic energy as it falls and picks up speed. Another example is a stretched rubber band. It has elastic potential energy stored in it, ready to be released. So, potential energy is all about position or state. Now, let's switch gears and talk about something that powers our modern world: electrical energy. This is the energy carried by moving electrons, which are tiny charged particles inside atoms. When you plug in your phone, you're tapping into a flow of electrons through the wires, delivering electrical energy to charge your battery. This flow of charge is what we call an electric current. We'll explore how this current is generated, from power plants to solar panels, and how it travels through the grid to reach our homes. It's a truly electrifying topic. But where does the energy in a battery come from? That brings us to chemical energy. This is the energy stored in the bonds of chemical compounds, like the atoms and molecules that make up everything around us. When a chemical reaction happens, these bonds can be broken and reformed, releasing or absorbing energy in the process. A classic example is burning wood. The wood contains chemical energy, and when it burns, that energy is released as heat and light. The food we eat also contains chemical energy, which our bodies convert to power our muscles and keep us alive. To really understand chemical energy, we need to zoom into the atomic level. Every atom is made up of three fundamental subatomic particles: protons, neutrons, and electrons. Protons have a positive charge and neutrons have no charge. Together, they form the dense center of the atom called the nucleus. Buzzing around the nucleus are the electrons, which have a negative charge. It's the behavior of these electrons, and how they form bonds between different atoms, that is the key to all of chemistry and chemical energy. Understanding these different forms of energy is just the beginning. One of the most fundamental principles in all of science is the law of conservation of energy. It states that energy cannot be created or destroyed, it can only be converted from one form to another. Think about a hydroelectric dam. The potential energy of the water stored behind the dam is converted into kinetic energy as it flows downwards. This kinetic energy then turns a turbine, creating mechanical energy, which a generator then converts into electrical energy. The total amount of energy in the system remains constant, it just changes its dress. This brings us to a very practical question: how do we measure energy and power? We hear terms like joules, watts, calories, and kilowatt hours all the time, but what do they mean? The standard unit of energy in science is the joule. A calorie, which you might know from food labels, is another unit of energy. One food calorie is actually a kilocalorie, which is equal to about 4,184 joules. Power, on the other hand, is the rate at which energy is used or transferred. The unit for power is the watt. 1 watt is equal to 1 joule per second. So, if you have a 100-watt light bulb, it means it's using 100 joules of electrical energy every single second it's turned on. Now, let's get a little deeper and talk about the second law of thermodynamics. While the first law tells us energy is conserved, the second law deals with the quality and direction of energy flow. It introduces the concept of entropy, which is often described as a measure of disorder or randomness in a system. The second law essentially says that in any energy conversion, some energy will be lost as unusable heat, and the total entropy of an isolated system will always tend to increase over time. This is why a perpetual motion machine is impossible, and why your room gets messy all by itself but doesn't spontaneously tidy up. This law has huge implications for everything from engine efficiency to the direction of chemical reactions. Speaking of chemical reactions, let's introduce another important concept, enthalpy. In simple terms, enthalpy is the total heat content of a system. When a chemical reaction occurs, the change in enthalpy tells us whether the reaction releases heat, which is called an exothermic reaction, or absorbs heat from its surroundings, which is an endothermic reaction. For example, a campfire is exothermic because it releases heat. An instant cold pack is a great example of an endothermic process. The chemicals inside absorb heat from their surroundings, making the pack feel cold. Understanding enthalpy helps chemists predict and control the energy changes in reactions. We see these principles at play all around us in nature. Take the water cycle, for instance. When the sun heats up the ocean, liquid water evaporates into water vapor, a gas. This process absorbs energy. Later, when that water vapor rises, cools, and condenses back into liquid water droplets to form clouds, it releases that stored heat back into the atmosphere. This release of energy is a major driver of weather patterns and storms. It's a massive, planet-scale example of energy conversion and enthalpy change. Finally, let's tap into an amazing source of energy right beneath our feet, geothermal energy. The word geothermal comes from the Greek words for earth and heat. Deep inside our planet, the core is incredibly hot. This heat radiates outwards, warming rock and water in the Earth's crust. Geothermal energy harnesses this natural heat. In some places, hot water or steam rises to the surface and can be used directly to heat buildings. In other areas, we can drill down and pump water to be heated by the hot rocks, then bring it back to the surface to generate electricity using steam turbines. It's a powerful, reliable, and relatively clean source of energy that holds incredible potential for our future. So, from the tiniest atom to the entire planet, energy is the universal currency that drives everything. We've journeyed through mechanical, electrical, and chemical energy, untangled the units of power, and explored the fundamental laws that govern it all. We've seen how these concepts explain everything from a falling apple to the weather, and even how we can power our world. I hope this journey has sparked your curiosity and given you a new appreciation for the incredible forces at play all around us. The world of energy is vast and full of wonders, and we've only just scratched the surface. Thank you so much for joining me on this electrifying adventure today. If you enjoyed this deep dive and want to learn more about the amazing secrets of our universe, make sure you hit that subscribe button and turn on notifications so you don't miss our next video. We've got so much more to explore together. Until next time, stay curious.